Hi, I'm Paul Battaglia, and this is section 12.3, the tangent line problem. I'm joined today by Gabe and Brittany, and what we'd like to do is take you through the lesson a little bit, show you how we can get students to kind of really discover what we need them to discover and really close in on some goals that we need them to achieve by the time we're done with section 12.3. Gabe, start us off. What do we want students to really come away with?
Sure. So by the end of this lesson, I really want my students to be able to work fluently with the definition of the derivative.
Right.
So I want them to know the definition of the derivative,
Okay.
maybe even have it memorized by the time we're done with this section,
Right.
and also know how to interpret it.
Okay.
So I want them to be able to think about the derivative as the slope of a tangent line.
Perfect. And you know, I think what we want is we want students to kind of bridge the gap, or we're trying to bridge the gap for them between the previous sections where we did the limit of the difference quotient and now, what does it actually mean? So, Brittany, tell us a little bit more about what we want students to kind of, how we want them to progress through the rest of the section.
So before even talking about, the slope of the tangent line and everything, I want to go back to chapter 1 and talk about secant lines and say that the slope of a secant line is the average rate of change.
Correct.
Well, what if we want to find, just one point in between those? We start moving them closer together, so we're creating a limit. And, well, what is that point? All right, well, now we've created a tangent line. And the slope of the tangent line gives us an instantaneous rate of change.
Which ties into the derivative.
Exactly right. So it's a new concept, a really neat concept. And we have to also keep in mind that what we're doing is, we're not covering calculus right now. So we're really trying to show them some tidbits, but some very important ones at that. So to do that, maybe they need a little bit of a visual aid. And so just give you an idea of what you can do with your class. So we have a couple materials here, very simple materials. Piece of paper, any size really. Marker or pencil or pen, some tape, and some dry spaghetti. Don't even really need a plate if you don't want. So every student should have these materials really. If you'd like to have the tape just available for students to come up and get during class, that's okay too. So here's what you want to instruct them to do. They don't necessarily have to mimic the curve that I draw or you draw. You just want them to draw some type of curve on their paper. So I'm going to do that. Okay, and tell them to fix a point somewhere. So let's suppose I just draw this point here. We'll call it point P. So that point's not going to move. So then what we're going to do is we're going to start far away from that point and just label it. I'm going to call it point A. So let's say I go right here. Call that point A. Now, why do we need the spaghetti? Well, the spaghetti, as Brittany said, is going to help us with our secant lines so we can visually see what's going on. So I'm going to take one piece of spaghetti, connect the 2 points as if I was just drawing a secant line right through them. I'm going to tape one end. I'm going to fix it to P. This way, my spaghetti's not rolling all over the place. Now, what I want students to do is, as Brittany said, I kind of want to mimic exactly what she said. I want this secant line to now get closer and closer to going through P, but with these points inching up this curve here. So I'll say, okay, let's draw another point along the curve as we get closer to P. So maybe we label this guy B. Okay, again, take another piece of spaghetti, right? Now go through point B and point P. Okay, fixate it again, so we're on top of each other there. Now, what I really am trying to point out to students as they do this is, do you notice a couple things? First off, the slope of that first secant line was, a larger number than the slope you're going to get here through the second secant line. What did we do in the interim? Well, it looks like not only did the horizontal distance, get closer to P, but also that vertical distance of this new point moved closer to P as well. And so what we're also trying to illustrate to them is that idea that, that average rate of change, right? We're trying to approach that limit now, right? What we're really doing is they say, well, how does this have to do with limits, right? Well, what we're doing is we're taking those distances between both the horizontal and the vertical distance, and we're collapsing that distance. We're having it getting closer and closer and smaller, and we can't make it zero, right? So we'll do it maybe one more time or two more times. So we draw another point, another piece of spaghetti. Another point, another piece of spaghetti. Until all of a sudden, and you can even take a smaller piece here, all of a sudden, if we try to kind of just stack that piece of spaghetti right there, as Brittany said, what we have done now is we've taken these secant lines and we've made them into such a way that this last piece of spaghetti or something very close to it is a tangent line almost, right? Now, could we do this using graphing software? Of course we could do that, but spaghetti's just more fun, So as we do this now, I'm trying just to get students to understand what Gabe said is, we are now approaching what we call an instantaneous rate of change. I like to end it with this. I like to show my students a video. And it could be any video of anything in motion. It could be a runner, or it could be a car driving along a track or something. And what I do is I show them a video, and sometimes I'll try and pick something like, just a really neat sporting event or something like that. And I'll stop the video. And I'll say, do me a favor. Tell me how fast how fast is this car going right now? And they'll actually shout out some numbers. 10 miles an hour, 25, 100 miles an hour. And I'll say, well, how do you know that? And then eventually you have a student say, well, we don't, because as you stop it right here, no distance is being covered and no time is elapsing. And I say, exactly. So the fundamental idea of a rate is that we should be able to do distance divided by time, and we can't do that here. So how do you talk about an object's instantaneous speed? You have to do this. You have to get to a time interval that's so small, that's such a minuscule amount of distance is being covered, but some is being covered and sometimes elapsing. And that, in essence, like Gabe said, that's a derivative. And I think it's very powerful. Like we said before, we're teaching an entire calculus class right now for students, but I think we're getting them motivated to really look into it a little bit further. I hope these tips have been helpful for you and you find much success in section 12.3.